We're going to start our electrical unit. We'll start with a few basic notes about electrical circuits. The overarching idea or equation for us is going to be Ohm's law. And the three variables are I is current, V is voltage, and R is resistance. Current is measured in amps, voltage in volts, and resistance in ohms. You've probably heard of amps or volts, maybe not ohms. A good way to think about circuits is to consider the electrical wires like a river or a water pipe. Voltage is the force that pushes a current through a circuit. Like for a river, maybe water falling down a stream or down a waterfall, the force is gravity. The more force, the more voltage. Resistance is the friction or something that's slowing down the flow of electricity. And an example would be, again, a river. The rocks in the bottom of this river are resisting the flow of water. They're slowing it down. Okay, so in electricity, voltage is the pressure pushing the water. The resistance is the wire resisting the flow, or the rocks resisting the flow of water. Current is just the actual amount of electricity that's flowing through the circuit, or the actual amount of water that's flowing. If you remember back to our whiteboarding earlier, we were talking about circuits and how to make a light bulb light. If you look at this one here, this should not work because it's not a circuit. The wire coming from the top of the battery to the bottom of the bulb is not a circuit. It doesn't allow the electricity to loop from one end of the battery all the way through and around to the other. So this shouldn't work. And this one, well, we certainly have the bulb touching the top. The bottom of the bulb is touching the top of the battery, and the wire is touching the side of the bulb. But the wire doesn't go around to the bottom of the battery to complete the circuit. It also is on the top, so there's no complete circuit. So this bulb should not light. This one, we have the electricity in the battery allowed to go through the bottom of the bulb, up through the filament, back down around out the side of the light bulb, and down to the bottom. So this is a complete circuit. This bulb should light. And so the central concept to all of this is that this is a circuit. The electricity is allowed to flow. And this is actually drawn correctly. The electrons will come out of the negative end of the battery and will loop up through the wire back down into the positive end. The negative electrons are attracted to the positive end of the battery. Circuit diagrams, there's a picture here with the batteries and a switch and a light bulb, but we don't really draw circuits with pictures or images. We just draw them as wires and little symbols. Now, a cell, the battery, is just drawn as it's pictured here in the lower left. It's got two vertical lines connecting the wires. If you look over on the right, the wires are just drawn. It doesn't matter the color. They're drawn red here, but that's not important. A switch is drawn like it is here, open, so this system would not actually be working because the switch is open. It's a break in the loop, in the circuit, so the electricity can't flow. And the lamp, or the resistor, is drawn as this circle with an X in it. And it could mean a lamp, a light bulb, or a television, a refrigerator, a microwave oven, anything resisting the flow of electricity. And a couple of simple circuits that we're going to study are series and parallel circuits. A series circuits are when everything is in a series, in a row. There's only one path for the electricity to go through. If you look at the top picture, if you remove one light bulb, well, then the electricity is stopped. The circuit is broken because the electricity doesn't have the light bulb to flow through. Let's say those light bulbs are in series. In the whiteboarding, you put the batteries in series. A parallel circuit is where there's more than one path for the electricity to flow in. So if you look at the bottom, Jeff, you'll see that if you remove one light bulb, it doesn't stop the others from lighting because the electricity has another path to get through there. These bulbs are parallel to one another. Now, how you measure current or amperage is used an ammeter, and we're going to do this in lab today, and we'll do it a couple of more times in other labs. And you simply have to flip the dial to measure current or amperage. The multimeter will also measure voltage in volts, and it will measure resistance in ohms. But for amps, we just simply need to turn it to the amp side of the dial. Now, measuring current, as you'll see here, the circle with the A in it, that would be the ammeter. For a series circuit, the ammeter is just put in line there. In a parallel circuit, it's still put in line, but you have to measure, the amperage is going to be the same. It doesn't really matter where you put it. Okay? So measuring voltage, the electrical push, the force pushing them, they're measured in volts, so the ammeter would have to be switched over to the voltage side. How you measure voltage is it's across the resistance, the lamp or whatever the load is, whatever is resisting the flow of electricity. The amp was put just in line in the wire, the ammeter. To measure voltage, you have to measure it on either side of the resistor. So you can see how much the voltage drops from one side of the wire across to the other. Measuring current, well, in a series circuit, current is the same everywhere. It doesn't matter how many light bulbs or televisions or cell phone chargers are plugged into that line, the amperage, the amount of current flowing is the same everywhere. In a parallel circuit, the amperage is shared. So here it's a 2 amperage system, but each offshoot, each one of the 2 parallel circuits gets, in this case, 1 amp because they have to add up to the total. If it was a total of 4 parallel lines, each of them would have half an amp, and any other calculation you want to do. So for an example, we're going to fill in the missing ammeter readings here. You can see in the first one it's a series circuit and it's 4 amps. Well, remember that amperage is the same in a series circuit. The current is the same, so it's going to be 4 amps everywhere. It doesn't matter that there are 3 resistors in here. It could be 2 or 1 or 7. It doesn't make any difference. For a parallel circuit over here on the right, you can see that there are 3 parallel circuits, 3 different places for the electricity to flow, and there's a total of 3 amps in this series, in this circuit. Well, remember that parallel, it's shared equally. The total amperage is 3, but each one of the branches is going to get 1, adding up the total of 3. So series and parallel circuits. Only one end of each component is connected in series. The electricity has only one path. That'd be like Christmas lights. You know that if one bulb goes out in your Christmas lights, the whole thing is gone. It's because it's in series. Parallel circuits, both ends of a component are always connected. There's more than one path for the electricity to flow. Like household lighting. If one light bulb goes out in your house, it doesn't mean that no other light bulb works. They're all on different branches. They all share the electricity. And there's more than one path for the electricity to get from the circuit breaker in your house to the different rooms and the different outlets and lights. So thinking about ammeter readings again, remember, in series, the current is the same throughout. In parallel, the current is shared. You're measuring voltage. Different cells, different batteries have different voltage. You know, your car battery is 12 volts, a little D or C cell, or a double A or triple A, or 1.5 volts. Different from your household voltage, which was generally 120 or 240 voltage. And unlike an ammeter that's measured in line, a voltmeter must be measured across the resistor. So from one side of the resistor, lamp, TV, whatever, to the wire on the other side. And this is called the potential difference. It's the difference in the voltage across the resistor. How much the resistor is resisting the flow of electricity, so it lowers the voltage across it. So in these, we have a in series one on the left. You see there's two lamps, they're in series. The voltmeter is connected across from one side of, and there's actually two voltmeters. It's measuring from one side of the load to the other. And the one on the right is a parallel circuit. So these two lamps are parallel to one another, but the voltmeters still have to be hooked up on either side across the lamp. And voltage is always shared. Even like in a series circuit, the amperage is the same in a series circuit. Voltage is shared in a series circuit. So this is a 3-volt battery, and these two lamps are in series. Each one of them is dropping the voltage, has a 1.5 volt potential difference across it. And in a parallel circuit, the voltage is the same in all. So measuring current and voltage are kind of the opposite. Remember, current is the same in a series, but is shared in parallel. But for voltage, voltage is shared in a series, but the same in a parallel. So it's a 3-volt battery system, and these two lamps are parallel to one another. The voltage across each of them is 3 volts. So measuring current and voltage, we have a 6-volt power supply, and we have 4 amps of current in this parallel circuit. So if we're looking to measure voltage in a series, the voltage is going to be shared. The current is constant. Everywhere you measure, the current is the same. The voltage is shared. In a parallel, it's sort of the opposite. The current is 4 amps total, but in parallel, the current is shared. So the lamp in the middle here gets half of the 4 amps, so 2, and the one on the bottom gets the other half, but they add up to 4. The voltage, however, in this parallel circuit is the same throughout. It's a 6-volt battery, so it's 6 volts across both resistors. Okay, so just to wrap it up here, 1 volt is a joule per coulomb. I know that's, you've probably never heard of those, but joule is the way energy is measured. Okay. So a volt is a joule per coulomb. An amp, the amount of current, is a coulomb per second. So it's how many coulombs are flowing in a second. So if I have 1 volt, a joule per coulomb, and 1 amp, a coulomb per second, then multiplying volts by amps gives me joules per second, or watts, because the two currents would cancel in numerator and denominator. The 2 coulombs would cancel. So So I'd be left with joules over seconds or watts. So how many joules per second is watts? And you've probably heard of watts, light bulbs and everything, and microwave ovens and hair dryers are always given in watts. It's a 60-watt bulb, a 1500-watt hair dryer, anything like that. So the formula for electric power, if you remember from the second slide in this video, from Ohm's law, power is voltage times current. And more work is done if it's done quickly. Higher voltage means more work is done. There's more power. Higher current means more power.